Hello, this is the last, fourth and final part of the chapter 5.1, and we will talk about the eigenvectors and the difference equation. And just to remind you that the difference equation is a recursing equation defined on the steps from 0 to k plus 1. And we say that the vector x at the say in the step k plus 1, the next step, is equal product of the vector x on the step k times the matrix A. And then, for example, of this vector can be the vector of monthly loan payments for the bank. For example, the vector x0 can contain the loans of all the bank customers. The first one can be John's loan, the last one can be Karen's loan, and there can be thousands of people in between. And for the next month, we will multiply this vector by the matrix A, which will contain the conditions of the loans, the previous payments, the missed payments, all this important information. And we will get the amount which John or Karen still own to the bank for the month 1. So if John or Karen call the bank and ask how much they will own owe to the bank in, say, 3 years, the bank have performed like 2 years, 12 months, 24 calculations to get this prediction. So it's kind of extensive. So our eigenvalue solution offer a shortcut for the difference equation. So there is a beautiful property of the difference equation matrix, which tell us that to find the vector x at the time steps k, all we need to do is define the eigenvalue of matrix A, lambda, raise it to the power k, and multiply it by original vector x0. That's it. So when John and Karen call to ask what's happened in 24 months, all the banker need to do is define the eigenvalues for the payment matrices, raise it to the power k, and in one calculation, give the desired prediction. So it's offer a huge speeds up in calculation. But of course, it's probably sound really strange, like too good to be true. So let's just test if that solution, xk is equal lambda to the power k of x0, is indeed a solution of a difference equation. Okay, let's start simple. Let's write down the solution for the first step x1 as our initial vector x0, which is the product of matrix A by x0. But we also, because we now have an eigenvalue solution, we can write it down as the lambda to the power k, which is 1 in our case, times initial vector x0. Oh, it's just lambda x0. Okay, that seems simple enough. So let's just calculate the solution at the step k, or product of matrix A times the vector at step k, A times xk. And we can again just start using our solution. Instead of xk, we can write it down as the lambda to the power k times x0. And we can easily, factor out lambda to the power k, because lambda is just a number. It's eigenvalue, but it's just a value, a number. So no problem factoring it out. And, then we will have a product of matrix A times the initial vector x0. And we can look at our previous calculation for the first month. We actually know that the products of matrix A times x0 will be just a lambda times x0. So why won't we replace this? Okay, so we have lambda here, lambda there. Why we will combine them together and write it down as a lambda to the power k plus 1 times initial vector x0. And that's by the definition of our solution. would be x k plus 1. You can practice by taking this solution in the blue box and putting x plus 1 instead of x, and you will find exactly the same values here. So we started as A, matrix A times x k, and we end up with our vector x k plus 1, the solution to the next time step. So it seems indeed our solution lambda to the power k times x0 is a solution. So we can use our eigenvalue solution as a shortcut.